Okay, so today we're going to talk about box plots and how to read a box plot. And you may have heard of this term or seen some box plots as a result of some data analysis. And it's a very clever, simple way to characterize a set of data to understand kind of the behavior, what it looks like and what we can tell from it. And to introduce it, I'm going to start with kind of a generalized distribution. Here's the typical Gaussian or bell-shaped curve, which can represent a data set, for example. And I've used what's called a standard normal in this example, which has a mean of one, or a mean of 0 and a standard deviation of 1. And from it, we know a lot of properties. Okay, and we know that, for example, 50% of the data will lie between 0.6745 sigma above the mean and 0.6745 sigma below the mean. Now this range here is called the forced spread, and it's actually important because there's a principle called Windsor's principle that basically says that the middle part of the data will generally be pretty symmetrical in nature. Okay, it's just kind of one of those rule of thumb type things. And we'll also utilize this forced spread to kind of get an idea of the variability in the data set itself. So these actually represent the box. So here's our box plot down here. Okay, so we're going to utilize this forced spread to kind of define this box right here. Then you'll also notice there's a line inside this box, and this is typically the median. So the median is a more robust measure of location than the mean is. The mean is very subject to outliers and influential values. So the box plot actually will plot the median value. Of course, if it's a very symmetric data set, the mean and the median will be the same. Okay, then we will define what are called fences. So we have an upper fence and a lower fence. So these are kind of like, in a way, the theoretical minimum and maximum values we might expect to see in a data set. And they're calculated by taking the upper fourth, okay, so this value here, and then taking the forced spread, okay, which was this range right here, multiplying this number by 1.5 and then adding it to this upper fourth, and we get the upper fence. And we do the same, subtracting, get the lower fence here. This is 2.270 sigma away from the mean, and this roughly represents about 0.4% of the data values in this tail, and the same over here. So this will help define any kind of unusual values. And indeed, if you get something out here, these show up as what are called outliers on the box plot. So sometimes you might see some values out here, and those are called the outliers. So that is basically how a box plot works. And you can determine some other interesting things. You can develop something called a pseudo sigma value. So if you want to kind of get a basic feel what the standard deviation is, you take the forced spread here, divide by 1.349, and that'll give you roughly a measure of the standard deviation without having to take the variance and then the square root and all that. So again, this is kind of the basic anatomy of a box plot. And if you're a little bit confused by the sigmas and the math here and all that, we'll just go into some examples, and I think it'll be a lot clearer. So here's an example of some histograms and an associated box plot. So for example, here we have a histogram of some data. Let's say it looks pretty symmetrical. These histograms are pretty familiar to most folks. And the box plot interpretation of this histogram is down below here. So again, you see the box that represents 50% of the data values, okay, right in here. And you can see it's pretty symmetrical, not a lot going on. The mean and the median, right about there, that's the median. But now you see the fences, upper and lower fences are here, and these would be the outliers. So these would correspond to these data values here. So now we've kind of flagged stuff in this box plot that we really didn't flag up here in the histogram. Okay. So this is kind of how the box plot works here. Here we have a distribution that's a little bit more skewed. And again, we have the box here, which represents the 50% of the data values. And you get the median here. You notice the median's a little bit offset from center here, which indicates a little bit of skewness. But generally, again, remember the middle part of the data should be fairly symmetrical. But the median is a little bit lesser. And you can see this whole box plot itself is shifted down a little bit. And we have quite a few outliers here, which correspond to these data values out here. So again, you can also determine, the shape of your distribution or your data from box plots and kind of see which points are definitely being flagged as something kind of unusual. The nice thing about box plots is you can compare them side by side. So for example, let's say I have this, maybe it represents some kind of test or something. So I have a box plot of the data values here and one of another factor here. And I can tell that just from the width of these box plots that maybe the variability here is a little bit less. You can see that this one is shifted much above this one. So factor B definitely has something going on here that's a little bit different than factor A. There are no outliers here. So that tells us also something about the underlying nature of the data. Now, since box plots have been around for quite some time, there are variations. Notch box plots. We have box plots in which the width of the box plot is proportional to the sample size, and a lot of other things like that. So, a lot of things have improved, have changed over the years in terms of box plots. But essentially, they're a great way to characterize a set of data. And, there's a lot of information out there. Any statistics package will generate box plots. And it's a great way to summarize a set of data compactly and provide a really nice, clean visual interpretation of what's going on. Hope that helps, and we'll talk to you again.